One of the pillars of a green future is electric power. So by 2030, many thousands of specialists and managers are needed in the battery sector in Europe. To prepare us for this task, we created a place to train these experts, our ELLB. Here, we empower battery experts with leading-edge knowledge to shape Europe's green future. ELLB, European Learning Lab Battery Cells, part of the Fraunhofer Research Institution for Battery Cell Production FFB.
My name is Phillip Suttmeyer. I'm the project manager for the academy activities at the Fraunhofer FFB, and I have today's honor to guide us to the following lecture. In the first 3 webinars, we already got some first insights in the European battery ecosystem, the material cycle of lithium-ion batteries, and in the sustainability of battery cell production and the digital twin. Today, it is our 4th webinar. The topic, forecast along the battery value chain. But before we start with our speaker presentations, I would like to give you, and especially those guests who missed the last lectures, a small overview of the Fraunhofer FFB and the European Learning Lab Battery Cells, ELLB. Also, I would like to present the webinar program and today's speaker. The Fraunhofer FFB is located in Münster. It is an open battery cell factory for research and development purposes, which claims to become the center of development of a modern and scalable battery cell production for Germany and Europe. This claim is also fixed in our value proposition called Innovations for an Efficient and Sustainable Battery Cell Production. To ensure that production in Germany can provide new battery technologies more efficiently, more cheaply, and in the highest quality in the future, the federal government and the state of North Rhine-Westphalia are funding the research factory for battery production with a total of 680 million euros. The factory will provide infrastructure for small and medium-sized companies, but also large companies and research institutions can test, implement, and optimize the near-series production of new batteries with a theoretical yearly production capacity up to 7 gigawatt-hours for electrode material. In addition to those technical supports for the upscaling of battery cell productions in Europe, a further aim of the Fraunhofer FFB is the transfer of battery knowledge to close future skill gaps. This is why the European Learning Lab Battery Cells was established. The demand of the ELLB is to empower battery professionals with leading-edge knowledge to shape Europe's green future. The responsible project team for this task unites the competence of 5 different Fraunhofer institutes, the Fraunhofer Academy, and also the Fraunhofer Alliance Battery, and ensures that everyone will find the right course and lots of knowledge on the subject of batteries. The targeted philosophy is characterized by the following claims. We focus a close cooperation with relevant European players. The development of our curriculum will be marked by the iterative exchange with industry partners and also with an agile approach to address changes in the market and quickly create added value. We will include our industrial production lines, for example through augmented reality applications, and offer virtually interconnected smart learning. We will also add innovative possibilities in training and curriculum, and also innovative learning environments based on the new work principle. Our first program on the market is a webinar series, which provides a short overview over these 4 topics. As already mentioned, we started with an overview about the European battery ecosystem. For all of you who missed this webinar session, there are some good news. You can find a recording on our website. The second webinar had its focus on the material cycle of lithium-ion batteries, the challenges that come along in the process of production, and an overview of recycling and its chances. The recording is also published on our website and our YouTube channel. In the third webinar, Sustainable Battery Cell Production and Digital Twin, we discussed sustainability issues in the classical lithium-ion battery cell production, as well as the use of digital twins. The recording will follow. Last but not least, today's webinar. The forecast of the battery value chain regards the political, strategic, economic, and social challenges arise in the future when establishing the battery value chain. Our two experts, Dr. Axel Thielmann and Dr. Lukas Weymann from the Fraunhofer Institute for Systems and Innovation Research, ESI, took a deep dive in the future possibilities of lithium-ion batteries and its value chain. Unfortunately, Thomas cannot participate due to illness. Lukas will also do his part. In the next hour, we will learn about the employment effects of lithium-ion batteries along its whole value chain. Further, we will have a close look on the chances and challenges along the whole value chain. And in conclusion, we are dealing with the political, strategic, economic, and social future of the battery sector. Afterwards, if you are interested, you are very welcome to join us for another 30 minutes question and answers with our experts and enter the discussion. If you like to address questions in the ongoing presentation, you can use the chat function in Teams. All questions will be saved and answered, at least in the following Q&A. I wish you all a good time and hope you will enjoy today's webinar. I'm now passing on to Axel and Lukas. Thank you for your attention, and now let's start the session.
Thank you, Philip. So let's start with the fourth and last webinar. We are very happy that we can be here again and give another presentation on some topics, because Axel and I already started with the first webinar and gave some overview about the whole battery ecosystem. So for those of you who weren't there, of course, you can rewatch, as Philip just mentioned, the presentation. But I want to just, and it's not very, you don't need the prior knowledge, of course, for this webinar, but I just want to start with two concepts that we've established there in November, in the first webinar, that we're going to use a bit for today. So the first concept is the battery value chain, which is just the value chain or the lifetime of a battery, starting with the beginning where the battery is built. So we need the raw materials for the batteries. Then we start processing some battery materials and components for the battery. Then the battery is really produced by being assembled to a battery cell. Then we will make with this battery cell some modules or systems and put these batteries into application like electric vehicles or stationary storage, for example. And in the end, at the end of the lifetime of the battery, we're going to recycle the battery again to get again raw materials to start the circle over again. So this is a simplified picture of the lifetime of a battery, of course, but something that's very useful to us. It's going to be useful to us today, especially. And this is also a second diagram that we discussed a bit in November. And I just want to go into the most important things. So this is presentation of the demand for batteries for the different battery markets. So batteries, of course, are being used in different applications. One of the biggest applications, as you can see by the large blue bar here from 2020 to 2030, is the electric mobility. So the electric cars we're going to use, maybe electric trucks or other applications, of course. We have the energy storage, which is the stationary storage systems, for example, to balance the grid, the electrical grid, or when we have photovoltaic on the roof, we're going to store energy there. And the 3C electronics, which is the consumer market. The markets are not too important right now, but what I want to show you is really this demand for batteries. So we have here this curve increasing till 2030 with a huge number of 660 gigawatt hours. I don't want to go too deep into that because we talked about that in the first webinar, but just I want you to remember that there's a large demand, and this is the forecast for the demand. And this is exactly where I'm going to start today. So today we're going to talk a bit about forecast and about the future of batteries. And I want to tell you, the last time I showed you this, no one actually asked, how can I say that this is going to be the demand? So now I want to justify a bit this forecast by giving you some insights in the methodology to get to forecast for the battery economy and forecast in general. So talking about forecasts in general, there's one very, very famous forecast, which is called Moore's Law, which I want to tell you about. It comes from microelectronics, and it tells us that the number of transistors, which is a very important device or part of a device being used for computers, that can be put on an integrated circuit, so on some microchip, for example, doubles every 2 years. And this is his diagram from his paper in 1965, so it's very old already. You can see he has just 5 points and then drew a line through it and made a prediction out of that, which is quite interesting because it's called Moore's Law, and usually we use this expression more in natural sciences. For example, we have some physical law, for example, that the energy stays the same in some systems. But this is more like an observation and prediction of the future. So this is called a law, even though it's more like an observation and a prediction. The impressive thing is that this observation was really turned out to be more or less true. So now you can see the number of transistors that are being put on a microchip from 1965, shortly after 1965, up to today. And you can see this increase. So this is now a linear increase. But when you look at the y-axis on the left side, you can see that we don't have the numbers going up from 1, 2, 3, 4, 5. But in fact, for each unit we go up, we see some tenfold number. So we go from 1, 10, 100. This is called a logarithmic scale. So in fact, this shows that we have some exponential increase of the number of transistors, which was exactly what Moore predicted in 1965. So this is a quite impressive forecast, of course, even though I still wouldn't call it a law, actually, because it's something that is still being developed and being made by human beings, and which give us this improvement. So this was you saw the picture before. He just said a few points and then drew a line through it. So it's really that simple to predict the future. We just take a look at the past and extrapolate this to the future. So we just say, okay, this increase will stay the same. Of course, it's not, especially when we talk about battery markets, like I showed you earlier. So what we discussed about is really the demand for battery cells. So how many battery cells can be sold? How many battery cells are demanded by the markets? For example, the car manufacturer who wants to build his electric vehicle. And for this, we use a more complex model than just drawing a line, of course, the Bass diffusion model. And of course, we extended this, but this is just this most simple form. And this is now the only equation I'm going to have in my presentation. So I hope I won't lose you here, and we're just going to go through it one by one. So on the left side of the equation, you see the sales. So what we're going to try to predict is the number of sales that are possible. And on the right side, we see some different mathematical terms. And yeah, let's just have a look onto that. So when we just start with a term to the very right, the remaining market potential, this is really just how many consumers don't have the product yet. So we can use this model for all kinds of different products, for example, electric cars. So for this equation, then we would say, okay, the sales are equal to the consumers who don't have the product yet. That would be the simplest form. Of course, it's not true, because not every consumer would buy an electric car right away if they don't have one. So we need some more terms. Then we have this innovation coefficient, which we multiply by this market potential, which tells us, which is some coefficient, so really just some number actually between 0 and 1, how many consumers that want to buy a product because they don't have it yet. So we say, okay, there are a certain number of consumers who don't have an electric car, and this gives us the percentage of consumers that want to buy the product now because they don't have it. So this is one part of consumers that buy an electric car. And then we have this very interesting second term, which I find actually fascinating, more or less, because it tells us a bit about, I think, how we work as humans. It's called the imitation coefficient. It tells us how many consumers want to buy the product because they see that others have it. So we really split the people that buy, for example, electric cars, but we can use this again for all kinds of products, into two groups. The one that buy the electric car because they think, okay, this is an innovation, I want to have it. And those who see, okay, others people drive around with electric cars, I think now I need to get one too. Again, it's a simplified picture, but this simple equation is already very good enough to get some first predictions about how a market develops, so how the demand for products develop. So you see now two curves. Let's start with a yellow one maybe, which is called the market penetration. And it tells us on the right, we have the axis which goes up to 100%. When we're at 100%, it means every consumer, everyone who could buy an electric car has an electric car. So that's what we reach at some point in the future, possibly. That would be one way how to describe the market. And we can see this curve. So on the x-axis, we have the time. We can see this curve increasing. So we start at no one has electric cars, then we see some increase. In the end, everyone has electric cars. And this can be translated into the sales as well with this equation, where we can see, okay, in the beginning there are only a few cells, and then in the middle, during the middle of the time, many people are buying electric cars, and at some point, the number of sales goes down because many people own already electric cars and there are less consumers who don't have it yet. Again, simplified picture, but this is really actually the basis for most of the models we use. This gets more sophisticated, of course, when we need to apply this. But I think this gives some nice insight about how it works. So we don't just draw lines through points and say, okay, what is your feeling how it's going to be? But we use some mathematical models for this. And why do we do this? Of course, it's very interesting to know how markets develop, how products will be adopted, when they will be adopted, to really see, okay, if I'm, for example, a battery manufacturer or a car manufacturer for electric cars, when do I need to be ready to produce electric cars so that I can really sell my cars on the market? And this diffusion, how we call it, the market diffusion, is this process where a product really gets diffused on the market, so it enters the market and then spreads throughout the whole market, is of course influenced by external parameters. So of course it's not that easy to just use one model and apply it, but there can be different influencing factors, for example, regulations that push the implementation of new products, or that also can decelerate them by implementing regulations that are so hard that it's not that easy to get for product to get on the market. And in the end, why we do this, of course, because we can support strategic decisions, as I described before. So we now want to look at a bit on the electric cars again, how it works there. I told you we can use this to make a forecast about how quickly electric cars enter the market and how this process will look like. When we want to talk about batteries now, we of course need to know the battery capacity in passenger cars. And this is another curve that I'm going to show you. So this is now not the prediction of the demand, but rather a technological forecast, which is something else, and it works a bit different, of course. But this is on the full line you see, which goes till 2022 roughly, is the line of battery capacity that we have in an electric car. So we can we have the data, of course. We can look at the electric cars that are being sold, and we can see what is the average battery capacity being built in this car. And we expect this battery capacity to increase in the next years. So here you see the line till 2030 to above 70 kilowatt hours. Why is this? Because, of course, when we have a larger energy storage in the battery, we can, for example, drive further distances, or we don't need that much time. We have more time until we need to recharge the battery. So this is a trend that we see. And when we have this data, so we can see, okay, how much capacity is in a car, we can extrapolate, or we can calculate the demand for lithium-ion batteries. So now you see three lines. The green line is the demand, so we have three different scenarios where we say, okay, if this is a slow process, we take a bit different assumptions. Then we change our assumptions a bit to look, okay, how would a fast adoption of electric vehicles would look like. So we have different scenarios, and you see the green line is the average line. And again, so this is now a global demand for lithium-ion batteries, and you see a huge increase going up to 10 terawatt hours, which is a huge number when we approach 2050. So what is a good forecast? Again, we just don't draw simple lines, but it's more complicated than that. We have market models, and it was very important to really use different scenarios. So we cannot say, okay, this is how it's going to be and this is how the regulation is going to look like, but rather we need to assume, okay, if this will happen, how will it look like in the end? So we vary our assumptions, and then with the sensitivity analysis, we analyze the effect of the assumptions. And in the end, of course, very important, the transparency, to really be transparent about the assumptions that you've taken for the forecast, so that other people know what's behind the forecast and can adjust accordingly. Okay, and now just to the final part of the first part. Why do we do it? Why did I show you the battery demand and tell so much about it and try to tell you how we get to the solution? Again, it's very important for us, and I want to show you 3 different questions that we can answer based on the assumed battery demand. One is how much investment is needed to cover the battery demand, which is of course very important for companies on the one side, but of course on the national or international level. So for the European Union, it's important, okay, how much investments are needed to set up battery plants? How much do we need to push this? How many employees will be needed for setting up the battery economy? Because when we set up the plants, of course, we need people working there, skilled workforce, and this need to be pushed before the plants are finished and they're up and running, and then there's no one there who can work there. So we need to know this beforehand. And another question that could be answered is how many raw materials will be demanded for the production? Again, the same reason, we want to know how much is needed, so we can adjust the policy, so we can adjust the mining or push the mining for raw materials before we have the plants that want to build batteries. So these are just 3 examples. I'm just going to give you the 3 answers to this according to our calculations. So some roundabout numbers, up to 100 billion euros will need to be invested by battery cell factories into battery cell factories. So those factories that take the materials and then build the electrode and the battery cell in the end. So this is quite a huge number in Europe and huge investments. And we're going to talk about this a bit later when we come to Axel parts. But now I also want to give you the job number. So more than 3 million jobs are needed along the battery value chain. Here, actually, for the cell manufacturing, this is a smaller number. I think it's around 10% of this. But along the whole value chain, especially when we integrate the batteries into electric vehicles, there are many people needed that are skilled workforces in this area. And the raw materials for Europe in 2030, we roughly need about 100,000 tons of lithium in battery cell production, which is a huge number again. And it's something, of course, that cannot be done in Europe because we don't have the access to lithium on that large of scale. But it gives us some feeling about at what order of magnitude we are. Yes, so this was the first part that we have here.
Yeah, thank you very much, Lukas, for your presentation. You also brought a question along. I think you quite good explained the complex mechanisms of market development, that not only the demand, but also the technology supply and other frame conditions are influencing such curves. And indeed, over the past years, we've seen very often that predictions have been corrected upwards. Meanwhile, again, we have a discussion if there will be a certain showstoppers which are influencing that. We will come back to that also in the discussion on the frame conditions and future challenges. The question you would like to ask here and we would like to discuss is the rapidly increasing demand for batteries we have seen. What our audience thinks about the technological improvements which are needed here. And here we would like to ask you to vote if it's needed to improve the battery technologies, so produce better batteries, or the battery production technologies, which means to produce more quickly the batteries, or is it the need for electric vehicles to use batteries more efficiently, or is it for battery recycling technologies to use better materials more efficiently? So we are quite interested in what you are voting for. Yeah. What are the most needed improvements?
I can see that the first answers are coming in, so you should all see now a place where you can vote on Teams. We already have 30 answers. Yes, and you can select multiple answers. Just select those which you think are the most important. You can select 1, 2, 3. If you want to, you can select all of them, of course, but we'd like to see the priorities there. Right now, I think we have 2 leading, or the leading answer is actually recycling technologies, which I think it is quite interesting, with nearly 40% who voted for this. And I could imagine that the reason for this is, of course, that there's a lot of space for technology improvement, and it's something that we don't have established yet, while we have conventional battery technologies and we are already building the first battery plants. And then on the second, I think I don't know if it changed right now. We have now the battery technology, so that the quality of the batteries needed to get better, with 29% and 23% the battery production technologies. So this would be the answer, or your answer of the audience, for how we can really deal with this demand that I was showing. So we looked at the demand and know that there's production possible, and you gave now the answer, I think. Yeah, the electric vehicles are on the last place with just 11% that we need their technological improvement.
So it's rather, I would say, rather the vote to improve the battery technology up to the cells, and not on the more demand side, or on the integration of the batteries into the electric vehicles. So question, of course, within your curves and scenarios you've shown would be, what kind of technology would that be that will drive this development in the future? I guess here you will show also additional insights that we now focus more on the future battery technologies which are ahead, and we can see there. And with that, I would like to ask you to take over the presentation that Thomas Schmalz would have held, and to start with the second part. By the way, questions can be answered later on. We will have a question and answer session starting at around 2 o'clock.
Yes, but of course you can put the questions into the chat already. Yes, thank you, Axel. So this is really now to dive deeper into the question we've just asked you as an audience. So we want to look at what are actually the technological improvements along the whole battery value chain. So that's why I started, of course, with it. And we want to just move around the whole value chain and look at the different technological trends that we see there, or the potential for technological improvement. Starting at the very beginning with the raw materials. And here we formulated 2 things. So one is really to make the extraction processes that are there already more energy efficient, to make it more sustainable in some sense for the raw materials we have. But also, and this is one of the big topic, the ways to extract lithium. So to find new ways to extract lithium in a more sustainable way, to extract lithium from water. This is where some technological improvements happen. Actually, I think we mentioned this already in Europe, for example, to get it out of water, or even in Germany, we have some improvements there, or some technological trends to look into that. So this really at the very start of the value chain. When we look deeper into the material and components now, we see 2 different trends, or we want to split this into. One is to make some progress with the lithium-ion battery technologies, the conventional technologies more or less. So the current battery technology, which is the state of the art, is a battery that is based on lithium ions, and uses a liquid electrolyte, and uses some graphite anode, for example, and then different cathode materials are being used. So these are the main components, and what we see is that these chemistries can be improved or changed. On the anode side, for example, we can use silicon anodes or silicon-rich anodes, which improve the storage capacity, so the energy capacity of the battery, or even lithium metal anodes, where we have really the material that the ions is from as a pure metal on the anode side. There are many difficulties so far because it's easy flammable, but it's already being used at some battery technologies to use lithium metal anodes, for example. And of course, there again, this would have the nearly optimal, this would have a very good energy storage capacity if we have just the material, which are the ions that we need for the energy transfer, or the charge transfer through the battery cell. On the cathode side, I want to tell you a bit later into more details. We see some new cathode materials that are being developed and are being improved with NMCs and NMCAs. I'm going to talk about that a bit later, but you also learned a bit about this in webinar 2. And for example, sulfur cathodes. And as I mentioned before, electrolytes is a big thing. So right now we use liquid electrolytes, but there's a huge or a very large trend of moving to solid electrolytes, which could give all kind of improvements. One improvement that's always being said, one advantage is that they could be more safe because we don't have the liquid inside the cell. But of course, this could also be used to achieve better, more energy, store more energy in the battery cell, so get to battery energy densities. Yes, and then already we have components for novel battery chemistries, which we put out on the third part, so for the battery cell. When we can think about batteries that are based on lithium ions and improve them, for example, by using a solid electrolyte or these different anodes and cathodes. But of course, we could also switch to different technologies, different ions that are moving. So we don't base the battery on lithium, but on other materials. We have a few named here, natrium, aluminium, zinc, which are all being researched. Probably right now, one of the hottest topic is the sodium. Okay, sorry, I said natrium because it's the German word for it is sodium ion batteries. So the Na stands for sodium here, because sodium is a very cheap material. I mean, it's very easy accessible, and we can build batteries that are way cheaper than before. And in the past month, there was a lot of development there. There's now the first car, I think, that was shown to be able to drive with a sodium battery. We see that, for example, in Germany, this is becoming a hot topic, and many researchers are adapting there to look deeper into sodium ion batteries. The downside is, of course, that they're not as powerful or have such a good performance or energy storage capacity as lithium ion batteries, but they could be cheaper. We also have novel cell designs, for example. So usually batteries are built in cylindrical cells, as you know from your AAA batteries, or in some pouch type cells or prismatic cells. And there are new cell designs right now with building mostly bigger cells. This is one large trend. Of course, this diversifies. Many different cell manufacturers have many different kind of cells. And one very important thing is improving the production technologies of really producing the battery cells. There we move to, or try to move to, more energy efficient processes. For example, right now when we build the electrode, we have some coating which is based on solvents. It's some wet coating, and to make this dry could remove the energy consumption when we want to dry this wet coating. So that could reduce, for example, the energy consumption during battery production. And of course, we want to have this all scalable and fast and clean. So we want to maintain a high quality there. Now I put this arrow in between battery cell and application, because of course, when we have the batteries, we need to build them, or we put them into a battery cell, into a module and a battery system before we put it into the car. And that we can look at packaging technologies and battery management system. But I want to tell you more about this a bit later. And in the application, of course, we have an increasing demand, which is a huge driver for the whole technological development. And we also have different properties that are being asked for in the battery cell from the battery. For example, a car needs different properties of the battery than, for example, when we have a stationary storage. This gets more complicated because a car can be used in different ways. You can drive long distances with it, or you can drive just through the city short distances. And even further, trend recently is to also use it again as an energy storage that is connected to the grid, which is a concept called vehicle to grid, where we can store energy from the grid or give back energy to the grid from our car, which is a concept which is quite interesting and being discussed a lot. But again, this also asks different things from the battery in the end. And of course, we can think about further applications like ships or small planes that are being researched, or just large street-based traffic like trucks. And before we get to the recycling, there's this whole second life business. So using a battery after it was in a car, again, in a second life, for example, as a stationary storage, which is something that is being tried out, and there's some development. It's being used and or being implemented by some companies already. We have the battery passport, which is a big development pushed by the European Union, where during the lifetime of a battery, all data or the whole environment or the data, the life of the battery is actually saved and stored digitally, so that at the end of the life of the battery, we can know, okay, what did this battery experience? We have the recycling in the end, where we have improvements of existing recycling processes to get more material out of the battery, and to also use novel recycling processes like direct recycling, so we don't just get the battery and we melt it down and then try to get the raw materials, but use components directly again. Or when we have the whole system of a battery, it would be nice to look at the battery cells which are still okay and which are not okay, and then use those again and recycle the others. So there's a lot of technology improvement. I want to shortly go into two things. One is this material components, one is the battery management system and the packaging. So this is something you've had in the second webinar, so I just show you the main things and go quickly through it. We have the graphite-based anode active materials, as I mentioned, which is the state of the art. In the future, the trend is to get more silicon, which you already see. So we don't have pure silicon anodes, of course, but we see that silicon nanoparticles are being used, for example, to increase the capacity, and the lithium metal anodes, as I told you before. More interesting are the cathode active materials, where we see that we move from NMC, which is being used a lot, which is nickel, manganese, and cobalt, to other chemistries. For example, LFP is something that's already being there, but it's used more and more, which is not as powerful, doesn't have that energy density, but we try to increase the capacity. Electrolytes, I told you already, so going from liquid to solid is there, the big change, and we have different solid electrolyte technologies based on different materials. So we have polymers, oxides, and sulfides, which are being researched on, and all are being improved, so they're going to be used at a large scale eventually. And this is something I mentioned earlier, the battery chemistries, we can think beyond lithium, for example, sodium or zinc or aluminium. For going through the cathode materials, here's a lot of information on this plot. I just want to show you this arrows that we have on top, really the trends. When we look at the cathode materials, this is the cost of the different cathode active materials. So we have the LCO, which is lithium cobalt oxide, and then we have this NMC where we have nickel inside, and the trend is always to reduce the cobalt content and use more nickel instead, because nickel is cheaper than cobalt. Cobalt cannot be gained that lot. Then we have the iron-based cathodes, the LFP and the LMFP. Well, the trend is different. LFP is cheap in the beginning, so you see the blue bar, LFP right here, which is cheap, and we try to make it more powerful by adding manganese and going to LMFP. So this is a big trend. For anodes, this trend is not as large. There's not that much change. So cathode materials are really being researched a bit more. And so the forecast here is for till 2030, how this share of cathode materials that are being used develops. And you can see that these NMCs with a lot of cobalt are expected to really drop and phase out till 2030. So we are below 10% for the high cobalt content cathodes. And we see some NMCs still going to be there, but with different mixtures of nickel and cobalt. Okay, this was a lot of information. One more, we have this whole packaging topic, and I need to be quick because I have a look at the time. One trend is, I told you that when we have the cell, we put it into the modules. When you look at the picture to the top here, and then we put the modules into packs. This is how it's conventionally being implemented, the battery cell into a car. Then we put the pack in the car. One concept to grow beyond this is to put the cell directly into the pack, because then you can save a lot of inactive passive materials, the packaging of the modules. And one step further, actually, which is not shown here, is the idea to put the cells directly into the car, which is called the cell-to-chassis design. This is something that's being researched again. And then for the system, we have the battery managed system, which actually handles the battery while it's being used. So it it says the electrical connections are being all more or less directed by the battery management system. And this is to improve the battery life of the battery, for example. So the life of the battery is based on how it's being used. So when it's being charged a lot and discharged a lot, and how deeply it's being discharged. So if we really go down to 0% of the battery or just to 20%, the temperature that the battery experiences, these are all things that influence the life of the battery cell. And by having a better management of this, that's why it's called battery management system, we can increase the lifetime of the battery. So really understanding how the lifetime of the battery is influenced and how to prevent this by using a good battery management system, we can really extend the life of the battery, which is of course good for sustainability. And with this, I directly will switch over to the question that we have in the end, and maybe I just read out, so we have enough time for Axel. So now I want to ask you, you've seen all the different developments. What do you think how the future of the battery technology is going to look like? Do you think that it will stick more to conventional lithium-ion batteries, which is the first answer that's possible? Or do you think that we have all kind of different battery technologies with different ions that will coexist? Do you think that the importance of ecological parameters will further increase and we get more green battery technologies? Do you think that the most important thing is the price? And so the price will determine what is the technology that is dominant in the end? Or do you think that material shortages will lead to accelerated developments of those alternative battery technologies based on alternative materials? So you can see these are not exclusive. You can, of course, select again different things. We just want to see what you agree with the most in the end. And I'm just going to fill this out by myself as well to see what we have in the end. But maybe, Axel, maybe you see the results and you can comment on that already.
Yeah, it's about going to start, but already we can see that the strong vote is for a large variety of different battery systems, if I see correctly. But also I see that there's quite a good share. So you can see that the questions somehow are also overlapping. That of course also the ecological parameters play an important role, as well as of course the price as a dominating factor. But if I see right, smallest votes are for the conventional lithium-ion batteries will dominate also in the future.
Yeah.
And it's a mix across the others. It's somehow a bit surprising. So I would have thought that many people will vote for the conventional lithium-ion batteries, although we have seen that there are a lot of potential alternative technologies around. And also we've seen in the first question with the materials and recycling aspects that the question for getting more independent on materials, on strategic materials, is a big issue. So the picture is quite broad across.
I think it's quite interesting to really see that everyone in the audience hopes for and expects more technology development. So we see some more diverse variety for the battery technologies, and we see some technology improvement. So again, how do we get there? And now we're gonna look at the challenges and the different strategies we have. I used a lot of the time already, sorry for that, Axel, but I think you also managed to get us through the different challenges in establishing a European battery value chain and give us some insights on the strategies being used by the different countries.
Okay, thank you. So we'll start then with the third part of our discussion, which now we had a discussion on the technology aspects and also kind of market aspects. Now I'd like to turn over rather to the different frame conditions in which it hopefully is possible to develop a European battery value chain. To start, I'd like to look at the historical development and what is our positioning as today. So in the past, Japan was a lead supplier, then of course together with Korea. And the lead market some 10, 15 years ago, when all the global activities around battery development for electric mobility started, the lead market was rather at Japan, but also in United States. It's totally turned over the last decade, more and more with China getting into the technology, preparing battery supply chain. But China here started from more lead market position. China is a huge domestic market with a huge need for batteries for electric vehicles. And therefore, the strategy went into this direction. And what we can see today is that in China, we can find basically all technologies along the battery value chain, and even more, China now is starting to expand its businesses globally across world regions. This is the situation we can see today. Of course, at the same time that we are in a phase in the next 5 to 10 years of a critical market development, as we've seen in scenarios before, it is important to position the different countries and actors along this or in this value chain. For that, different countries are reformulating or again strengthening their policies with policy documents. For example, in Japan and Korea, there are strategies and strategic documents around tending more towards being competitive and a leader in supply. In China, there are both policies. China tends to be autonomous and also is expanding to other world regions. And especially the United States at the moment with the so-called Inflation Reduction Act, which is a huge investment package in order to reindustrialize the American industry, is now a policy measure which normally intends to go against the Chinese position, but also impacts, of course, the European position. Here in Europe, we have also strategic research agendas and huge debate about technology sovereignty and what can be done or what can be the counteraction or measure from a European perspective. If you look at the different countries and their strategies in Japan, at first we can say that it was an early technology leader and had a strong focus on the supply side, but now reformulates its strategies. For South Korea, similar to Japan, coming from this technology leadership, strongly influenced by the private sector with large Korean conglomerates and like the cell makers. We can see here like Samsung, LG and others. And in China, we have seen this shift from the demand side to the supply side policy, and now with the expansion plans towards other world regions. In Germany, quite recently, a new DACH concept from BMWF, for example, has been written and is out, which now focuses more and more on key performance parameters and but also looking at alternative battery technologies. And at the core, not only for Germany, also for Europe, the focus is on upscaling and the production processes. For Europe, the European Union, we can see that the sustainability of a battery value chain with the so-called battery directive, which sets also targets to recycling quotes and so on, is approaching a countermeasure rather from a sustainable perspective than only from a cost competitive or direct perspective. It's more indirect measure. And therefore, ambitious and concrete sustainability goals are set, and that against the Inflation Reduction Act and the strategy that the United States or the policy the United States is currently showing. On the next slide, we ask what are the potential measures for Europe that can be undertaken. And here, typically, we divide along four kind of factors which are influential. One is the knowledge and the R&D. Another one is, of course, cost and competition. A third one is the market structure, so supplier, customer relations. And the fourth one are the frame conditions. For the knowledge and R&D, Of course, potential measures are to adapt the research funding instruments, what we've seen with the so-called important projects of common European interest, for example. But also here in Europe, we have a more structure with SME. But we do not have, like in the United States or other world regions, huge startup scene. That could be something could be more pronounced. Also, IP strategies from science to industry, as well as education and training, so creating a skilled workforce, are potential measures. For the cost competition, of course, public investments are playing a role. I noted the IPCEIs, but also looking at the United States with the Inflation Reduction Act, huge grants and subsidies are provided to industries in order to industrialize production in that region. Also, of course, scaling, saving through infrastructures like test beds, but also the energy infrastructure is a huge topic, and also digitalization could help to reduce the costs. For the market structures, we are in a phase of, again, partnerships, joint ventures along the value chain. It's pretty much under discussion that the cooperation with European companies along the supply chain is important in order to cover that within Europe, but also maybe non-European business can be attracted towards Europe. And references to build supplier relationships are of importance, of course, for newcomers, for new entrants. If the alternative markets and technologies are the largest one, that's something which is under discussion or can be discussed also with respect to which alternative technology might address which market and could be of interest in future. On frame conditions, we have with the battery regulation or battery directive something ongoing, as said before, looking strongly at the sustainable issues, which then makes sense, of course, with such quota and including CO2 footprint and so on, not to ship batteries around the globe, but localized production. That's, of course, something which is in favor to have a more localized ecosystems. But besides that, still this regulations has to start and has to get concrete. And along that, a big issue is, of course, the bureaucracy, which still needs to be reduced, but also maybe technical standards and other issues are potential measures for increasing improving the frame conditions. So that's a number of different potential measures to make it more concrete. What especially for Europe is under discussion are the most effective issues. One topic, of course, is the capital expenditures, CapEx, and the investment conditions, which have to be supported in order to get a level playing field. I mentioned the IPCEI, which is comparably low amount of money compared to what are the investments in United States. Also, the time is quite long. That's criticized somehow. It took about 3 years to build and prepare the battery IPCEIs, which are around. Whereas in the United States, it's mentioned that this happened along only a few months, up to 1 year. But those subsidies can help to create a level playing field in a critical moment. Another discussion, of course, is the energy price, which especially in the last year have increased or almost doubled in Europe, which is increasing the gap to China and United States and also has somehow to be corrected. So international cost competitiveness is needed. The next one is, of course, to ensure and protect local value chain creation. All the discussions we have around is very much on the importance to create a European value chain with European actors as well in order to be somewhat independent and technology serene. And as mentioned, battery directive is in preparation. It's about to concretize, but also access to the different technologies, starting with raw materials, is needed. Last but not least, also skilled workforce is needed, and which means that especially here for electric vehicles coming from the internal combustion engine, a lot of people have to be or upskilled. But also we need know-how here in scaled battery production, which has been so far built up in Asia, but not in Europe. Those are, from our analysis, the more concrete factors and which could be part of a counter strategy from Europe. But of course, we would again be interested in your opinion, in the opinion of the audience. And with that, with our last question for today, we would like to ask you, what measure do you think is the most urgent, which has to be undertaken? Is it technology funding? Is it improving or increasing the subsidies and grants to support the investment conditions, so to build up the infrastructure? Is it to address the energy costs at an international competitive level? Or is it rather on regulations and measures to create a EU supply chain, or a reduced bureaucracy or skilled workforce? And with that, I'd like to hand over to Lukas for our wrap-up discussion. And of course, we are aware that several of those points or all of those points are of importance, but maybe there are tendencies and looking forward to what's coming out.
Thank you, Axel. Yeah, sorry for taking that much time before, but I think we just cut it by a few minutes. And I think this is a nice start of the final discussion. So yes, please fill out again the last poll. What do you think is the most important factor here? So now it's actually single choice. I actually see that already more than 30 people already answered, which is quite interesting. While we look at the answers, just feel free to put your questions into the chat. I think we have also technical support by Caro. I think you will be there somewhere to check if in the chat there are questions coming up. Perfect. But let's first look at the results coming in. I think we have now more than 40 answers, which is already a good representative insight in the audience's feeling what's the most important factor. And actually the energy cost with 29% was nearly 1/3 of the answers, which is quite a lot, which is interesting, especially due to the past month, of course. It's quite a hot topic, with the follow-up being reduced bureaucracy, which I think is also quite interesting because we see, or we need to talk, or we do talk about that a lot in Germany and the European Union, of course, where we have a lot of bureaucracy for the larger projects, especially for the IPCEIs, for example. I think, Axel, you can say a bit more to that, the bureaucracy involved there, or how long it takes for IPCEIs to being realized after the first plans.
Yeah, that's what I mentioned in one of the points, that here we see that, even there was an IPCEI on microelectronics before, where I understood that it took even up to 5 years when to start, and now it reduced to 3 years. So its processes need to be need to speed up such processes. But I think it's a quite consistent picture. We can see here that the cost issues, energy costs, to subsidize, to create a playing field, and the bureaucracy are the three most important issues. And it seemed that, like the regulations to create the supply chains, or what we meant with the battery directive, is of importance as well. But more urgently, it seems that those cost relevant factors like energy costs down and speed up with reduced bureaucracy, as well as the subsidies at a higher level, seem to be the three most important factors here.
Yes, quite interesting. I think we're going to talk about that a bit more. I just see that Phillip also turned on his camera. So maybe before we dive deeper into this discussion, we started already, you want to say a few last words, I think.
Thank you, Lukas. Thank you, Axel. Thank you for interesting presentations and your given insights. Also, great thanks to the huge number of interested participants joining us today. So we are a little bit over time, but now we reach the end of our lecture, and we will stop the recording. Right after, we start with a casual Q&A with our two experts for further discussions and networking. So feel free to contact them. And hopefully we will see you again in the next events. And thanks again for your interest, and a good day to all of you.